So now let us try to do a problem. Yeah. So now let us move on to the first part of this question, which is the computation of the value of VB. Okay. So choose the value of VB such that my M1 is 50 millivolt away from triode. Now, what does it really mean? Now, we know that in order to have a current, okay, so the current value is given that the current that is flowing throughout the entire circuit, right from VD to the ground, is defined as 0.5 milliamperes. Now, in order to have this current flow through M2 transistor, obviously we need a particular value, a single value of VGS. Okay, and let me mark that single value to be equal to VGS2. Okay, now, and as I said before, I said that the value of VB is basically it's a potential that I have across the gate to the ground, right? So now this potential basically splits across two different components. One is VGS2, the other one is across the VDS2. Okay. Now, according to the statement, it has been stated that my transistor M1 has to be 50 millivolt away from the triode. So what I have across my, I keep repeating the same mistake, it is VDS1, sorry. Yeah. So what I really mean by this particular top statement is that the current value of VDS1 is nothing but the minimum value that it has to have in order to stay in the saturation region, which is VOE1, plus there is a 50 millivolt extra that has been added upon the value of VOE1. Okay, so hope that it is clear, and this is nothing but our Q point value. Okay, so having this as my Q point value, let us try to evaluate the value of VB. So for which I basically need to compute the value of VOEs of both the transistors. So generally one could use the expression of this VOE to be square root of 2ID Kn dash and the appropriate value of WL factor of either M1 or M2. Okay, so I'll just write down the results. By making use of this expression, a VOE1 would end up having a value which is equal to 0.27 volt, and a VOE2 which turns around to be equal to 0.61 volt. Okay, now from this value of VOE2 I could extract the value of VGS, right? So it would be like VGS2 is nothing but VOV2 plus the threshold voltage, and since the gamma is considered to be equal to 0, there is no body effect, so I'll retain the value of VDH that is given as 0.7, and I substitute over here, and that turns out to be a 1.31. Okay, so that is the voltage that I have. So rather I just try to add up each of these expressions or each of these values onto this expression, so that would end up having a value of VB that is equal to 1.63 volt. Hope I have not done any mistake. Yeah, because I have to still include this 50 millivolt. So it is just the VGS2 I have computed, VOE2 I have computed, but along with this I also have to add up this 50 millivolt towards it. Okay. Yeah. So now that we have computed this, and we also got to know that whatever the value of VDS1 that I have is nothing but it serves as my Q point at this node. Okay, just because we know the current that flows through the circuit and the resistance value is known, and I try to evaluate that as well. So which is defined as VDD minus ID times RD. So I guess the ID value is 0.5 and the RD is 1K. So what I have is just 0.5 here, and this is 3 volt, and the Q point that I have is just 2.5 volt. Okay, across the output. Yeah. So now we'll just move on to the second part of our question. So the second part of the question is to calculate the small signal gain of this entire circuit under the assumption that the capital GM could be approximated to be just GM1 itself. Okay, so I think with a negative sign. Yeah. So now under this condition where I have approximated the value of this transconductance of the device as just the transconductance of my M1 transistor, one could write that the gain is nothing but it's a product of GM times R out. So where in the place of GM I substitute that to be equal to GM1 into the R out. So again R out could be evaluated just by looking from the drain of M2 transistor. I am looking at a resistor across the source of M2, and that resistance is nothing but my RO1. So the resistance that I have between the drain and source of M1 is basically RO1, and that when I look through the drain of M2, we know that it gets magnified. Okay, so we'll use that concept for the downward direction. Okay, so currently I denote that expression as Rx, which is GM2 RO2 RO1 plus RO1 plus RO2. Okay, so this is my expression for the Rx, and when I look up, it obviously what I have is just RD. So I have this RD in parallel with Rx. So we have to perform this computation right now. So the computation is again has to be carried by knowing the value of GM1, GM2, RO1 and RO2. What I do is that I'll just quickly write down how to basically compute the value of GM with a common expression, which is 2ID Kn dash W by L. So I can make use of this expression to compute both the value of GM1 and GM2. So if I do so, I will end up having a value for GM1 to be 3.66 millisiemens and the value of GM2 to be equal to 1.638 millisiemens. Okay, so these are the two values I would get just by making use of this formula and the corresponding value of WL factor in them. So what is left over is just the computation of ROs, right? So according to the question, the value of RO could be computed just by knowing the value of lambda, and for both the device the lambda is given as 0.1. So I can just make use of this RO, which is defined as 1 by lambda times ID, and the same goes with RO1 and RO2. So whatever I compute for RO1 is the same value it goes for RO2 as well. Okay, so based on this I have both the value of RO1 and RO2 both to be equal to around 20k. Okay, so that is the resistance that I have, and again I'm not going to perform the entire computation. The only thing that I do is compute the value of Rx separately and then later on substitute it back. Okay, so the value that I would get would be around so this one turns around 655k, and this one individually 20k and this one individually 20k, so they add up to 40k. So this is the total summation that I have, and the value of RD is given as 1k in the problem. So I have this whole huge value of resistance in parallel with 1k resistor. So 1k in parallel with 695 kilo ohm. Okay, so that turns out to be somewhere around 998.56 ohm. Okay, yeah. So now that you could able to see, even though I have a very large resistance when I look down, just because we had a very small distance at the top, the entire resistance at the output has been stepped down. So what is the shortcoming of this particular value of having an R out being small? The shortcoming is basically the gain that I would get out of the circuit will also step down, just because the gain is directly proportional to the R out expression. Okay, so if the value of R out is stepping down, obviously I would lose the gain that I would get out of the circuit. Okay, so we'll try to rectify this by replacing this RD with some sort of active device once I complete this particular problem. Okay, so let us hold this that there is a kind of shortcoming just because of this resistance RD onto the gain. Yeah, so we'll just continue our gain computation, where when I try to multiply both these quantities, I would end up having a gain value which is minus 3.66. Okay, so this is the value that I would get as a gain right from V in to the V out. Okay, so right from here to here is what I've calculated right now. Now we will move on to the C part of our question. So with the value of VB that was calculated from the part A of this question. Okay, so compute the magnitude of input signal that can be applied over the input Q point such that M1 stay in saturation. So it's a quite lengthy problem, and this is where I'm just going to connect whatever we discussed regarding the swing. Okay, yeah, so the whole point is that how would we compute the magnitude or the peak value that I can have across the input signal? So first of all, we need to know that there is some sort of VGSQ. Okay, that is what has been defined. Okay, so there is some sort of VGSQ that I have, and over which so because of this VGSQ, I have a current whose value is 0.5 milliamperes. Now on top of this VGSQ, what I have is a small signal, and so I'll just try to express in terms of graph. So I have a VGSQ base value, and on top of this I have a swing, and let me read the magnitude of this particular swing as Vi hat. Okay, so that is the magnitude that I go all the way up and down. Okay, so as I said before, what is happening is that when I try to increase the value of like when I'm currently at the top, the current value of VGS that I have is basically the VGSQ plus this magnitude Vi at the top. Okay, so that is the current value that I would have for this VGS. Okay, so at this instant in time. Okay, so this VGS is defined as VGSQ, or this particular node value is defined as VGSQ plus this Vi. Okay, the only thing that is being asked is what is this maximum value that I can have. So in other words, what I'm trying to read is V in max. Okay, now how would I get down to this? Is there any data that I can use in order to compute this whole thing? Because somewhere this delta Vi cannot be directly computed, right, until there is some sort of information is available for us. So the way that I can compute this VGSQ is pretty simple. Just because I've got the value of current that is flowing through the device, which is 0.5, and we also know that both the transistors M1 and M2 are currently operated in the saturation regime. I can use this current equation, which is K dash W by L of 1, and there is something known as VGS minus VT, okay, or basically the VGSQ, and that's supposed to be equal to 0.5. So among this expression, we know this the value of VTH, which is I guess it is 0.7, and the value of W by L factor, which is basically equal to 100, okay, which is 50 by 0.5, which is basically 100 here, and the threshold value of the device is 0.7, and I got this value, and even I know that the K in dash is basically 1 point. I think I have to have enough space, so half 1.34 into 10 to the power minus 4. Okay, so I've got almost all the values that is required. The only unknown that I have is this VGSQ, which when I plug in here, and after doing a simple math, I can get down the value of VGSQ. Okay, so again we did this earlier in the part A itself, so that turns out to be a VOE1, which we computed, which was 0.27 is the value that we computed, from which I can just compute the value of VGSQ, which is VOE1 plus VTH, so 0.27 plus 0.7, and basically they both add up to get us a value of 0.97 volt. Okay, so that is the VGSQ value that I have in order to have a current flow of 0.5 milliamperes. Yeah, so the only unknown in this case is this Vi. How would I identify this small peak or the magnitude of this particular signal that is swinging around this particular Q point at the input. You have to remember that the question had a beginning, that I had defined the value of VB, which is said that my M1 is away from the edge of saturation by a factor which is equal to 50 millivolt, right? So I'm going to use this quantity or in order to read out our value. Okay, yeah. So whenever there is a positive peak, we know that from the base value of this Vxq, I'll be stepping down, right? Now, what is this minimum value that I have to have across the drain and source of M1? And this turns out to be my VOE1. So whenever there is a positive peak or V in max, I have a Vx minimum. Okay, so I guess one could use this simple relation as something like V in max is related. V in max is basically my VGS, and that could be related to my edge of saturation expression. My VGS minus VT has to be equal to my. So whenever there is a rise in this potential, I am reaching a maximum value. For this corresponding value, I have a VDS value which is currently right now the minimum value across the node X. Now, what is that minimum value that I can have? Is nothing but my VOE1. Okay, so from according to the graph, I can get down to this maximum just by adding my VGSQ plus this input magnitude, which is Vi hat, minus the threshold voltage. And how I can get down to this value is that we know that, so there is a gain from this node to this node, and whatever the peak that I have, there will be a corresponding magnitude of output voltage swing that I have here, and this magnitude can be read as a gain from this point to this point into the signal peak Vi hat. So what I really mean by that is that the magnitude of this particular swing that I have across this node is defined as the gain from the gate of M1 to the drain of M1 as A1 times that of Vi hat. Okay, so in order to reach to this minimum value, I have to subtract from the base value, which is Vxq minus the gain A1. We had to compute this A1 times that of Vi hat. Now, again, with respect to this Q point, how far away I am away from this edge of saturation. So that could be read from this statement. Okay, you could be able to see that from the base point, I am away from the edge of saturation by 50 millivolt. Okay, so which means that I have a swing here, and the magnitude of this swing is basically 50 millivolt. Okay, the lower swing. After then, what I have is just VOE1. Clear? So it's basically a VOE1 and then a negative swing, and that negative swing is basically my 50 millivolt. Okay, so with that in mind, I know that this value is basically equal to 50 millivolt. The only thing is that in order to compute this Vi hat, if I know the gain, I could identify what is the maximum value of Vi hat that I can have across this input Q point. Okay, so let us use that. So if at all, if I could able to compute what is my A1 times that of this Vi, which is supposed to be equal to 50 millivolt, then it becomes easier for us to compute the value of this Vi hat alone, right? So I'll just make use of that. So now when I look here, it's just a simple CS amplifier. Okay, so the gain of the circuit, which is defined as A1, is nothing but GM1 would be my capital GM times that of R out. So in order to compute the R out, I have to look down. When I look down, I'm looking into the drain of my M1 transistor. So that gives me an answer which is equal to RO1. But when I look up, I have completely a different resistance, right? So let me try to build that. I have an RD and there is a transistor M2, and currently I'm looking up through this M2 transistor. So what would happen to this RD term? Whenever I'm looking through the source terminal of a transistor, we know that this resistance RD would then be diminished by a factor of the intrinsic gain of this M2 transistor, right? But the actual formula has to further expand it with this extra terms to it. Okay, so this is the upward resistance that I have, but when I look down, what I have is just Rho1. So I have this Rho1 in parallel with this quantity that I have, which is Rd plus R0 divided by 1 plus Gm2 Rho2. Now this is the gain that I have right from this input to this Vx. Okay, it is not the gain from here to here. So please try to remember that. So after plugging in all these values, I'll just write down the final expression of it, which would be equal to minus 2.156, and that is the gain that I have across them. Okay. Now once I get the value of this A1, I just substitute here, and from here I could compute the value of Vi hat to be equal to 50 millivolt divided by this gain, whose value is 2.156. Okay, so that gives us a value which is equal to 23.19 millivolt as my peak value that I can have across the Q point at the input. Okay, so the maximum peak that I can have is just 23.2, okay, millivolt. Now let us move on to the last part of our problem, which is the D section. The compute the VO max and VO minimum for the computed value of Vi. Okay, yeah. So now, what are the value that I have computed? Because we got to know that the maximum swing that I can have across the Q point is this quantity. When I have such a small quantity of swing across it, let us see whether this small quantity stretches out the swing across my output to all the way down to VOE1 plus VOE2, and the peak value or the positive value to stretch all the way to VDD or not. Okay, so let us try to think about it and try to identify some sort of drawback in this structure. Now one could obviously write a VO max as something like VDD or basically V out Q plus the total gain. I'm talking the total gain right from the input to the output. Okay, so I think I have my circuit. Yeah. The total gain from right from here to here, that is the AV term, or I will write it as AT in order to denote the total gain times the Vi hat. Okay, is that is making sense? I'm just trying to read out the maximum value. So the magnitude of this particular peak is nothing but the gain plus the Vi swing. Okay, and similarly one could also read out this V out minimum as the Q point minus this magnitude, which is V out Q minus the total gain times that of my Vi hat. So when I try to read, when I plug in the value of Vi and this gain, the total gain which we computed earlier in this B part, which turns out to be equal to 3.66, right? Yeah. So this was the value we have got, and we also know the value of this Vi hat to be equal to 23.2 millivolt, and we also computed the value of this V out Q to be equal to 2.5 volt. Okay, so these are the base values. Now when I plug in all of these quantities, I would get a maximum value of V out to be equal to just 2.585. Okay, it is not equal to VDD. Okay, which is supposed to be 3 volt. So, and also when I try to compute the value of V out minimum for the given value of Vi hat, it is just turns out to be 2.415 volt, and this quantity is not equal to VOE1 plus VOE2. So if I could able to recollect, our VOE1 was 0.27 plus VOE2 was 0.61. Okay, so even when I try to add up these quantities, they never go past beyond the value of 1, right? Yeah, so basically what is happening is that based on the value of VB, I have a particular swing across my node X, and that in turn define the value of input swing. If I violate, then my transistor M1 might enter into the saturation regime. But for the entire swing for whatever it is being defined over here, my Vout node is swinging, but it is not stretched all the way towards VDD, nor it is not stretched all the way to the minimum value, which is VOV1 plus VOV2. Okay, is that is making sense? So obviously one has to think about like what exactly is happening, or how exactly one could define the value of VB. Now let me even define the same with respect to the graph that we plotted for Vout versus Vn. Okay, now basically what I've done is that we had fixed our Q point, our Vxq, somewhere closer to the value of VOE1. Okay, and the difference is just 50 millivolt. Okay, so now the way that I can think is that one could argue that I could raise the value of this Q point more than this, such that I can eliminate this issue and I can have a better swing at the output, where it can go all the way, stretches all the way to VDD, and this bottom swing of my Vout can all the way stretches down to my VOE1 plus VOE2. So basically, in order to have the swing, a full range of swing, I basically have to shift this VB. Okay, now when I shift this VB, what is happening to the graph is that previously I had, for small value of VB, I had this kind of graph. When I try to raise the value of VB, what I'm trying to do is that I'm trying to shift this bottom graph to a new value of this graph. Okay, so when I do so, what possibly could happen is that just by trying to increase the value of VB, I'm also trying to increase the value of my VOE2. Okay, so let me talk about this rise in the value of VOV2 when I try to increase the value of VB in tomorrow's class, because I know that the stream has gone past more than one and a half hour. So I'll just stop my stream. Thanks for listening.